In this video we're going to cover the near side. Now in the near side we only do subtraction with cancellation. So if you go to the resources section, you can open up the Excel spreadsheet, make sure you're on the tools tab, and then you can select add subtract. Now we're going to pick two numbers for cancellation. Now the numbers we're going to pick are the number 8 and the number 7.999, and we're going to subtract these off. Now this is the results we're going to get here, so what we want to do is stick them into the tool and see if we actually get these results. So let's go ahead and we'll stick those in just now. So if you go ahead and open up the Logisim file in the resources section and make sure you're on the top level. Now we'll put the values in that we've just seen, and as a reminder you can see that these are the values here. So we want to put this one in for X and this one in for Y, and we should get this as the output. So let me go ahead and I'll put those in just now. So we're going to have 41000000, and the other side here we're going to have 40FFF7CF. Now you can see here that we're going to subtract, so we have to click on this and you can see that we get the answer, and it's just about discernible. It's 3A832000, and that's the same as we've got in from the spreadsheet. So we know that this subtraction is actually working. Now let's go down into the add subtract, and I'll actually leave it at that size because it's easier to see. So we know that we're going to be doing a near side subtraction because the value for EX minus EY, that's the difference between the two exponents, is less than 2, and also we are performing a subtraction, so both of those have gone high, and we'll see those just in a minute. So if both of those have gone high, it means that the output here is high, and I've inverted this so the output is low, so it's going to choose the near path here. So we don't have any issues with chasing up truth tables as we did in the far side. The choice here is simply going to work through this test here. Now each of the components here, again the splitter, forget about this for the moment, we'll talk about this in the next video, but the splitter, the exponent difference swap, and now we're coming down this near path here, the addition of the hidden bit, which is the 1 here for X and Y, and also the 1 bit shift, and the MX minus MY, the leading 0 count, and also the EX minus leading 0 count, and concatenating them. All of these are modelled within the Excel spreadsheet. So what we want to do is we want to go into each of these and we want to compare each of the lines here to the lines in the Excel spreadsheet. So we can open up the Excel spreadsheet and we'll still have the two values that we put in. So we're going to have the 8 minus the 7.999. So the value of 8 is our X value. So that's this line here, and the value of Y is this line here, so that's the 7.999. So we're actually subtracting off the 7.999, so we actually get the sign value as a 1. But again, we'll talk about that in the next video. Now we have to ask whether the value for EX is less than the value for EY, that is the exponent for X is less than the value of the exponent for Y. In this case it isn't, and you can see here, if you note down at the bottom, I've got both the exponent values here. So the exponent for X is a value of 130, exponent for Y is a value of 129. Now we simply get those by taking the exponent value here and then taking away the value 127, which we use in order to create the biased exponent. So either way, the difference between these two values is just going to be a value of 1. And you can see that here, ex minus ey is a value of 1. So we know that the exponent for x is greater than the exponent for y, so we don't need to do any swap. So it means that this line here, row 2 is the same as row 5, and row 3 is the same as row 6. And again, we can see that in the adder and subtractor. If we head into the exponent swap, and again it works through the choice, and you'll see from this choice, if you check the values, you'll see the value of the input for the sine, the exponent, and the mantissa are the same as the output for the sine, exponent, and mantissa. That is, there's not been any swap. We've seen that in the previous video. Now the next part is we add on the hidden bit. In this case, the hidden bit is a value of 1. And again, that's quite straightforward. We can see that in the spreadsheet. We add on the hidden bit. So the hidden bit for this here is a value of 1. So we get 1, and then the point would be here, and then it would be all the 1s. And again, the hidden bit here, we would have a 1 point, and then the rest of these values here. So that would be a 24 bits. Again, we've seen this in the previous video. Now if we head back into the Logisim file, you'll see here we've also got this 1-bit shift. Now this 1-bit shift is the same as the shifter we see over here, and we use that 1-bit shift in order to ensure that the exponents values are the same. Now, as we mentioned, that the exponent values for the near side can have a difference of either 0 or a value of 1. If they have a difference of a value of 0, then there won't be any shift here. But if there is a difference of a value of 1, which we do have in this case, then there will be a shift of 1. So if we head down in here, we can see that we have the exponent shift here. Now in this section here, we're going to have our value my, so either the mantissa for y comes straight through to the output, or the value for the output is the value of my, but it's going to be divided by a factor of 2. So we test and see whether the ex minus ey is equal to 1. And this is the test here on the comparator. Now if it is, then we shift the value of my down by a factor of 2. That is, it's going to be a logical right shift. So either we get the value my passing through, or we get the my divided by 2. So in this instance here, you can see here that there is an equality. That is, the value ex minus ey is a value of 1. So it means we're going to have to shift the value for the mantissa, that is, divide it by 2. Now we're having to do that because obviously we're having to increase the exponent value by that same factor of 2. And you'll see that whenever we actually go through the example later on in the video, and I'll work through the actual numerical values. So that's the shifter here, and it gives us the value for our my out, and you can see that also in the spreadsheet. So we head into the spreadsheet, you can see we're going to have our value for our y, and you can see here that in order to ensure that they've shifted to the right position, we're going to have to take the y value and we're shifting it right by 1. So instead of starting with 1, 1, 1, it starts off at 0 and then 1, 1, 1. So this is the logical right shift, which is the mantissa divided by 2. So let's head in and we'll continue with the Logisim. Now you can see here the next one down, we've got the value of mx minus my. So we're looking for the modulus of this value. So if we head down inside, we'll see what this is doing, and we'll also look at it in the spreadsheet. So we're going to have a value for our mx and our my. And we said that if we're going to subtract off the mx and my, then we have to ensure that we're going to subtract off the smallest. This will allow us to have a 2's complement value, which just looks like a normal binary value. So this here tests for the smallest. So if mx is, in this instance here, it says if mx is greater than my, then we get this value here comes out as a 1, which means it then picks the value of my. So if the value for mx is less than my, then this goes to 0, and the output it chooses is just the mx value. So it's always just going to choose the smallest between those two values. Now we're also going to have to take out this extra factor here. Now we had to use this extra factor in order to ensure we got the right value for the sign. So we did mention previously that if we were to subtract off one value from another and it turned out we had to swap these round about, then we had to take a note of it in order to ensure we get the right sign, and this is at this point here. So here's the 2's complement for the smallest. We take the smallest and we put it through the inverter, and then we add on the value of 1, we get our 2's complement. Now finally, we're going to have to add both of these together. So let's go and we'll have a look in the spreadsheet first of all, and we'll see where we've got to. So at this point here, we've had to find the smallest. Now in this instance, it's quite simple because whenever there's a 1-bit shift, the smallest is always going to be this value over y, because it's always now going to start off at 0, and this one will start off at 1. So we take the smallest, and this is the smallest here, and we then invert it so it becomes 1, all zeros, and then we add 1 on and we get the 2's complement. Finally, we're going to have to add on the other value, which is either the mx or the my value. So that's this line 17 here. So we head back in, you can see here that we're going to take the value mx, my, and then we're going to add on the other value. So it will either be the mx or the my, depending on whether we've had to swap these. And this just gets chosen from this MRNS. So if this MRNS has gone low, has gone high, then at this point here we invert it, it will go low and it will choose the mx. Alternatively, it will choose the my. So finally we get our output here for our MR out, and this MR out is this value here, and you'll be able to see that in the actual spreadsheet. So if you head into the spreadsheet, you'll see these are all zeros and there's a 1, 0, 0. So if we head into the spreadsheet, the actual output here is, well, these are all zeros all the way along, and it gets to the 1 there, and then it's 0, 0. So this is this line here, which is the addition. So let's head back in and we'll continue. So we're nearly done. Now finally, we're going to have to look at the leading 0 count and the shift. So before we go and do that, I think what we could do is we could actually go through the numerical example, and then we'll come back to this little section, because the numerical example will make it very clear why we're continuing working through in this process. So let's look at the actual numerical values. If we were to put in our two values, which we were looking at, so it's going to be the value of 8, and it's going to be minus 7.999. Now equally we could write this as 8 plus just the negative value, 7.999. So we're just taking away, we're just adding on the negation here. So we could put these two values into the tool and we can chase up and find out what they look like in terms of our floating point mantissa and the exponent. So we'll go ahead and do that just now, and I've actually already done that. So I've taken this value here, okay, and I've also taken this value here, and we can put it in, and I'll show you where to put it. So we press close, and you get into tools, and you get into binary to decimal annotated. Then you can actually put the values in. So for example, the value of 8 is this value here. And you can see here, if you work down, 8 is nothing other than 1 times this value here, 1 plus 0 times 2 to the 3. So that's just 1 times 2 to the 3, which is what we expected. Now we can put the other value in for the minus 7.999 into this tool as well. And I've already done that for us, and you'll see it here, and I'll show you it just now. So these are the values here that I've actually put in. So you can see here that the value 8 is nothing other than 1 times 2 to the 3. Whenever I put in the value for minus 7.999, then this is the over here, and again you can put these in yourself if you want, but that's going to give us the value minus 1.99975, this number here, times 2 to the power of 2. So that's this one here. So we can actually have a look at that, those two numbers. So that's those two numbers here. I've put them up here as a reminder. The 1 times 2 to the 3, and this minus 7.999 is this number here. So you can see that if we subtract one away from the other, then we're going to have 8 plus the minus the 7.999, which is 1 times 2 to the 3 minus 1.99750181 times 2 to the 2. Now this is where we start working through our floating point arithmetic. We cannot subtract these until the exponents are the same. We take the exponent for the largest one, which in effect is our x value, and then we take the exponent for the smallest one and make it equal. So we're going to have to add 1 onto this exponent to make it a 3. When we add 1 onto this exponent, we're going to have to decrease this mantissa, that is, we're going to have to half it, that is, shift it to the right. So that's a logical shift in terms of the binary values, it's a 1-bit shift to the right. So we've done that here, and we're going to have this value here minus this value. The exponents are the same. Because the exponents are the same, we can simply subtract the numbers. So when we subtract the numbers, we're left with this number here, times 2 to the 3. Now you can see here that this number here is not in a normalised format. We're going to have to normalise that. But before we do that, we can see here that if we were to multiply this out in terms of the decimal, you would see that that is in fact that number there, which is approximately equal to 0.001. But the process here, the normalisation, what we're going to have to do is get a number here that's between the value of 1 and just less than 2. So to do that, we're going to have to shift this here up by the leading 0 count. So we're going to have to shift this 1, 2, 3, 4 places. So in effect, we're counting 4 leading zeros. That's including this one before the decimal point. So there's 1, 2, 3, 4. So it means that the value for the mantissa is going to have to increase by a factor of 2 to the 4. But if this increases by a factor of 2 to the 4, it means that this value here is going to have to decrease by that same factor 2 to the 4. So that we're going to have the mantissa going up by the leading 0 count, and we're going to have the exponent going down by the leading 0 count, and that's what we'll just have a look at now in the Logisim. So we can see here we've got the leading 0 count and shift for the mantissa. So if we drop down inside this, we're going to have the value for our result for our mantissa, and we're going to have to shift it by the leading 0 count. Now to find the leading 0 count, what we can do is we can use this find high. So if you click on it, you can see it's a bit finder, and I believe the bit finder, here's a bit finder, is in You'll find it in one of the sections here, so possibly in arithmetic. And let's see, bit finder. So there's the bit finder here in the arithmetic section. So what we can do is we can find the highest one, and then we can take off the value of 23 from it, and it'll give us the leading zero count. And you can see again that in the spreadsheet. If we were to go back into add subtract, we're looking to find the leading zero count, which leading zero count here from this value here is going to be this one here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's going to be 13 leading zeros. That is, we're going to have to shift this up 13 in order to get the mantissa in the right position, and we're going to have to decrease the value of the value for the exponent by that same value of 13. So if you were to head in and stick in the probes into each of the sides here, and you'll see that this little section here will give you the leading zero count. So this here is going to be the shift of the MR by the leading zero count. So that's going to be a logical left shift. That's the number's going to become bigger by this leading zero count. And finally, we take the output here for the MR and we take away the 24th bit, which is the hidden bit, and it gives us our final value here for our MR out. So that gives us the value that we require for our mantissa. Now, in order to get the value we require for our exponent, we're going to have to take the leading zero count away from the value of our EX. So that's the value for our EX there, that's the exponent of X, and we're going to have to take away the leading zero count. So that's the leading zero count here, and it's a value of 13, and we're going to have to take it away from EX, and it'll give us the value for our exponent at the output. So there's quite a lot involved in this video, and you can take your time and work through it yourself. Stick the probes in all the way through and compare the position of the probes with each of the lines in the spreadsheet. And finally, we join each of them together, the exponent, the mantissa and the sign, and the value heads out through the path. Now, I'll talk about the sign in the next video. I don't want to get into the details here, and the sign was mixed up as well with this add subtract button, so we'll go into that in the next video. Quite a long video, but take your time, stick the probes in and put some values in yourself, and it'll all become clear. And another thing to do, it's really handy, is whenever you put the values in your add and subtract tool, get in and put it in also to this binary to decimal annotated, so you can put the actual zeros and ones in, and it'll show you how the number is generated in terms of the sign, the mantissa and the exponent, and that is really useful and handy for understanding what is happening. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.